In this episode, we're going to talk about state management, which is one of those topics that sounds abstract until you realize it's the difference between automation that behaves like a careful librarian and automation that behaves like a guessy intern. When automation tries to enforce a desired condition, it needs a way to understand what exists right now, what it previously created or changed, and what it should do next to move toward the target. That understanding is what state provides. Without state, the automation may repeatedly try to recreate things that already exist, or it may fail because it cannot reliably match a definition to a real resource, or it may change something unexpectedly because it misidentified what it is managing. State management is the set of practices that keep that mapping reliable. When state management is correct, the phrase desired means something concrete. It means a stable, identifiable target that can be compared against reality and enforced consistently over time. When state management is sloppy, desired becomes a vague hope, and automation outcomes become unpredictable. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Start with the simplest idea. State is the memory of what the automation believes the world looks like, especially the parts of the world it is responsible for. In many systems, state is a record of managed resources and their key attributes, like identifiers, locations, and relationships. It's not the same as the code that describes desired state, and it's not the same as the live environment itself, but it connects the two. Desired state definitions tell you what you want, and the live environment tells you what exists, but state tells you what the automation has already associated with what it wants. That association matters because real environments often contain objects that look similar, and names are not always enough to uniquely identify them. If the automation can't reliably identify the thing it meant, it can't safely decide whether to update, replace, or leave it alone. The operational outcome of good state management is stable identity over time, which is the foundation for safe reruns and safe remediation. In other words, state helps the automation avoid making the wrong change to the wrong object. To see why this matters, imagine two environments with resources that have similar names, similar settings, and similar roles, but slightly different histories. If you only look at the desired definition, you might assume the automation can just apply it and everything will line up. In reality, the environment might already contain a resource with the right name but the wrong identity, or there might be two copies of a resource because of past partial runs, or there might be a manually created resource that resembles what the automation would create. State helps the automation distinguish between this is the exact resource I manage, and this is a similar resource that happens to exist. That difference is huge operationally, because updating a similar but not managed resource can cause outages, compliance issues, or confusing drift that's hard to explain later. Good state management makes automation more conservative in the right way because it ties changes to the specific resources the automation owns. Ownership, in this context, is not a human concept. It's a mapping concept that keeps the automation's actions precise. A common beginner misconception is that state is just a cache, and you can ignore it if things seem to work. That assumption falls apart the moment you need to handle change safely, especially when resources must be updated rather than recreated. If automation doesn't remember what it created, it may treat every run like a first run, which leads to duplication or conflict. Even worse, it might decide that the only way to reach the desired state is to replace resources unnecessarily, which can cause downtime and data loss. Correct state management reduces unnecessary churn because it lets the automation recognize that a resource already exists and is the one it previously managed. It can then calculate a smaller, safer set of changes to reach the new desired state. Operationally, this means fewer disruptive replacements and more targeted updates. It also means you can trust plans and change previews because they are based on stable identity rather than on best guesses. Another critical part of state management is understanding that desired state is not just a list of settings. It's also a set of relationships. Systems are connected, and resources often depend on each other in specific ways, like a service that depends on a network configuration or an access policy that depends on an identity. State often stores these relationships so the automation can update dependent resources when something changes upstream. Without that relationship memory, automation might update one thing but fail to update related things, leaving a half-correct environment that behaves unpredictably. This is where beginners sometimes get confused because they see automation change more than they expected, but often it's making necessary follow-on changes to keep relationships consistent. Correct state management makes those follow-on changes predictable because the automation can see the dependency graph it has built over time. It also makes troubleshooting easier because you can reason about why a certain change happened. It happened because the desired definition changed and the state recorded that this dependent object is connected. The operational outcome is fewer hidden surprises and more understandable change behavior. State management also ties directly to drift detection because drift is defined relative to desired state, and desired state enforcement often depends on knowing what the automation believes it manages. If someone changes a managed resource manually, drift detection compares live reality to desired definitions and to the recorded state, then determines what must change to restore alignment. If state is missing or wrong, drift detection can become noisy or misleading because the automation might not know whether a drifted resource is one it should correct. In the worst case, it might adopt a resource unintentionally and start managing it, which can surprise teams who thought that resource was out of scope. Correct state management helps automation draw clean boundaries around what is in scope and what is out of scope. Operationally, boundaries are safety features because they prevent automation from reaching into areas it shouldn't control. When boundaries are clear, drift detection becomes a trustworthy signal rather than a source of anxiety. Now consider the risk of state getting out of sync with reality, because that is where many operational headaches begin. State can become stale if changes happen outside the automation. If a partial run updated some resources but didn't fully update state records, or if state storage was lost or corrupted. When state and reality disagree, automation can behave unexpectedly because it is making decisions based on an incorrect memory. That is why state storage must be treated as a critical asset, not as an optional convenience file you can regenerate casually. Treating state as critical means controlling who can change it, keeping it consistent, and protecting it from accidental edits. It also means ensuring that team workflows coordinate changes so two different runs don't race to update the same state at the same time. When the team treats state as shared operational truth, automation becomes safer because decisions are based on a consistent view of what is managed. When state is treated casually, teams end up with conflicting actions and confusing outcomes. Correct state management also includes how you handle changes to the desired definitions over time. When you refactor definitions, rename components, or reorganize modules, the automation still needs to recognize that the underlying managed resources are the same ones, just described differently. If state mapping breaks during refactoring, the automation might think old resources are unmanaged and new resources must be created, which can trigger replacements you didn't intend. Operationally, this is one of the most dangerous moments, because refactoring can look like no functional change in code while causing large functional change in behavior. The safe approach is to manage transitions explicitly, ensuring that resource identity remains stable across code changes. The general idea for beginners is that renaming the way you describe something should not automatically mean destroying and recreating the real thing. Correct state management ensures that desired still maps to the same real-world object unless you explicitly choose to replace it. This makes automation stable during normal maintenance and evolution of the codebase. It's also important to understand how state supports the concept of planning and predictability in automation. When an automation system can compare desired definitions, recorded state, and live reality, it can often compute a set of actions needed to converge. That computed plan is only as trustworthy as the state data it is built on. If state is correct, the plan can be reviewed and relied on because it reflects real identity and real relationships. If state is incorrect, the plan might propose creating duplicates, deleting the wrong object, or making large changes for no good reason. In operations, this distinction matters because teams often rely on the plan as part of change control. A predictable plan lowers risk because you can catch dangerous changes before they happen. Correct state management is therefore not just about the automation engine. It's about the team's ability to make informed decisions about changes. In that sense, state management supports governance as much as it supports technical execution. A useful way to think about desired in the presence of state is that desired is both a target configuration and a target ownership model. Desired means the system should have certain properties, and it also means the automation should be the responsible party for enforcing those properties. State is how the automation knows it has that responsibility for specific resources. When you use state correctly, reruns become safe because the automation can recognize which resources to update and which to leave alone. Repairs become possible because the automation can identify drift in managed resources and remediate precisely. Team workflows become smoother because there is a shared record that prevents duplicate creation and conflicting updates. Even troubleshooting becomes clearer because unexpected changes can often be explained by state relationships and dependency tracking. The operational outcome is that desired becomes a stable, enforceable claim rather than a loose wish. To close, state management is the practical bridge between intent and reality, and using it correctly is what makes automation reliable over time. It gives automation memory, identity, and relationship awareness so it can decide what actions will actually move the environment toward the desired condition. It keeps boundaries clear so automation doesn't accidentally manage the wrong things, and it makes drift detection and remediation more trustworthy. It reduces unnecessary replacements by preserving resource identity across reruns and refactoring, and it supports predictable planning that teams can review confidently. When you treat state as a critical shared asset and keep it consistent with the live environment, you give automation the ability to understand what desired really means in a concrete, operational way. That's the difference between automation that stabilizes systems and automation that accidentally creates chaos while trying to help.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.